Welcome to another coding tutorial, and in today's video I'm going to show you how to simulate these natural patterns using a differential line growth algorithm. A differential line growth algorithm is a process that mimics how structures grow at uneven rates due to its surrounding factors, which result in these organic and complex shapes. And this kind of growth can often be found in nature, where we see it in things like plant branches, coral reefs, leaf veins, and even our brains. And that is why it is commonly used to simulate beautiful natural patterns. And one of my favorites is the work by the generative design studio Nervous System, and I'll put some of their work on the screen right here. To simulate the differential line growth pattern, we first need to understand what a node is and how it behaves. So a node is a point in space that represent a part of a growing structure, each with its own position, velocity, and acceleration. And each node moves based on its environmental factors, and so in this case, it's the nearby nodes. To control these movements, we're going to be applying the steering behaviors, specifically cohesion and separation. So cohesion ensures that the nodes stay close to their neighbors, creating smooth connections, while separations make sure that they're not too close to each other, preventing overcrowding. And as the structure grows, new nodes are inserted if the gaps between existing nodes become too large, keeping the growth process smooth and organic. And this iterative algorithm allows the pattern to continuously grow until stopped. This video is part of a series on Quadtree and flocking simulations. We'll be implementing the steering behaviors to control the node movements, and then at the end, I'll show you how to apply the Quadtree data structure to optimize the performance of the program. So if you have not seen those two videos, I recommend that you watch those to get a deeper understanding of these concepts. We're going to start by creating a class called node. So let's go to this arrow here, click the plus sign, and then click create file. Let's name it node.js. And then let's go to index.html and reference the file. All you need to do is copy and paste this line of code, change this name to the name of your new file. In my case, node.js, and we're ready. All right, let's go to node.js, start with the word class. I'm going to name my class node, and then inside the constructor function. As I mentioned before, each node is going to have its own position, velocity, and acceleration. So those are the three variables that I'm going to create. And these I'm going to set them as vector objects, which are an object that can hold 2 to 3 values. We're going to use them to hold two values, the values of position, velocity, and acceleration. So this dot position will be equals to create vector. So create vector is a method inside a vector class that allows us to create a vector. And if you put in two arguments, x and y, these are going to be the initial values. So I'm going to set x and y as the two parameters here. And then for velocity, it's going to be set to 0. So if you don't want to give initial values, you don't have to provide any arguments, but I'm going to set it as 0, 0, which is exactly the same thing, but you'll see why I do it this way in a little bit. And then for acceleration, it is going to be the same thing as velocity, which is vector of 0, 0. Next, how about we just write a function, a method called display, and just draw out a node. So it is going to be an ellipse, and an ellipse function takes in a total of 4 arguments. The first one is the x position, the second one is the y position, and then the third and the fourth are the size, the diameter. So let's set it to be 5, 5. I'm going to fill it with the color black. And with this simple set of code, how about we create just one node inside Sketch. So I'm going to declare a variable called node, and then inside setup, we're going to set node to be equals to a new node object. And for the x and y location, let's put it in the middle of the canvas. So width divided by 2 and height divided by 2. And then inside draw, I'm going to call the display function so that it draws out the node. All right, so nothing super exciting, but now we have a node in the middle of the canvas. So how about we go back to node.js, and now I'm going to write a new method called update. And basically what we're going to do inside update is that we're going to move the node around by adding vectors together. Velocity is a change in position and acceleration is a change in velocity. So basically what we need to do is that we need to add acceleration vector to the velocity vector to change the value inside the velocity vector, and we're going to do the same thing to the position vector by adding it to the velocity vector. So first we're going to add this dot velocity, and we can use a method inside a vector class called add to add the acceleration vector to the velocity vector. And then after that, we're going to do the same thing to position by adding this dot velocity. And go back to sketch.js and then call node.update. And if we click run, nothing happens, and that is because we set velocity vector and acceleration vector as 0. But let's say that I change this value here to 1. What's going to happen? So right now, the node is moving to the right 1 pixel at a time, right? So basically, the velocity stays constant at 1, but the position is changed by 1 pixel at a time. But let's say that I change this back to 0, but instead, I change the acceleration to 1. So now I click run, and then, as you can see, it speeds up to the right, right? So how about I print the x value of all of these vectors. So this dot position dot x, this dot velocity dot x, and this dot acceleration dot x. And as you can see here, the position is changed over time. The velocity also changed over time, right? It starts at 0 and then it just keeps growing, while the acceleration stays constant at 1, but because the velocity vector is updated over time, meaning that the change in position increases over time, and that's why we can see the node speeding up to the right. Then now what I want to do is that I want to go back to Sketch, and instead of just creating one node, let's create a bunch of nodes. So we're going to create an array of nodes, and then we're going to create a new variable called num. Let's set it to, how about we start with 10. So what I want to do is that I want to create 10 nodes that have initial positions around a circumference of a circle. So inside setup here, what I'm going to do is that I'm going to use a for loop that goes from I equals to 0 to I less than num, I plus plus, and then it's going to be nodes of I, right? And then it's going to be a new node at a specific location of x and y. So what are those x and y location? So what we need to do is that we actually need to convert from polar coordinates to Cartesian coordinates. So we're going to be giving a variable radius and the angle theta, right? And we can use trigonometry and set x to be equals to r times cosine of angle and y to be equals to r times sine of angle. And we're going to set r to a specific radius that we want. Let's do 100. But what should the angle be? So the angle will be an angle that is between each of the points, right? The nodes around the circumference. So we first need to calculate what is that value that can space out the nodes evenly. So it's going to be 2 pi, which is 1 revolution of a circle, divided by the number of nodes that we want. So 2 pi divided by num. And then we want to multiply it by I, so we know where it should be on that circumference. And so now we just put x and y here. And then we're going to write the same for loop inside draw so that we can call update and display nodes of I, nodes of I. All right, let's click run. Whoa. All right, we don't want to update the position for now. And as you can see here, the x and y coordinate is based on the origin point that is at the top left corner of the canvas here. So we want to move this origin point to the middle here. So we can just add the offset here. All right, and you can change the size here to be whatever you want, right? For the radius, and then also the number of points. Next, what we're going to do is that we're going to write a function called insert. And insert is a function that will insert a new node between existing nodes if the gap between the two nodes, the neighboring nodes, are too far apart. So first, what I'm going to do is I'm going to set num back to 10, and then I'm going to create a new variable. Let's call it distance, insert distance. How about we set it to 10? And then inside draw here, we're going to put in an insert function, which we're about to write. Function insert. So this function basically first is going to look at all of the nodes inside the nodes array. So let me just write a for loop that goes through the whole thing. Nodes.length, I++. And what it's going to do is that it's actually is going to just compare the two neighboring nodes. So this one and this one, or this one and this one, and so on. So I'm going to create two variables, n1 and n2, and set it to be equals to the current node. So nodes of I dot position, and then n2 will be nodes of I+1 dot position. All right. And then once we have these two positions, what we want to do is that we actually want to create a new vector. And this vector is basically going to tell us the direction and magnitude between these two vectors, n1 and n2. And we can do that by using vector subtraction. So I'm going to create a new variable called diff. And diff is going to be a totally new vector. So we can use the method called p5.vector.sub. And this basically allows us to create a new vector by providing two vectors that we want to find the direction and magnitude between them. But the position at which we provide these arguments matter. So what I want is that I want a direction that points from n1, this one, to n2, which is the one next to it, right? So to do that, I actually need to provide n2 as the first argument and then n1. So with this, diff is pointing from n1 to n2. And you see why I do this. So after we have this, we're going to write an if statement that says if the magnitude of this diff vector, so we can do diff.mag, is greater than insert distance. So if the magnitude between these two, so if the gap is too large, basically, then we want to insert a new point. But the point that we want to insert is actually in the middle. I want to insert it in the middle between these 2 points. So first, I'm going to multiply the diff vector by 0.5 to get the midpoint between these 2 points. And then now what I'm going to do is that I'm going to insert a new point in between these two. And the reason I wanted to have a new vector diff that points from n1 to n2 is that I can get the right direction, because the new node that I'm going to add is going to be in between these two nodes. Because if I were to point it a different way, then the node would be added in the wrong direction. So now what we need to do is that we need to add it to the nodes array, and we can use a function called splice to add that node, that new node. So all we need to do is put the name of the array and then the function splice. And splice can take in arguments in different ways. The way that we're going to do it right now is that the first one is the index at which we want to insert this new node. And it is going to be inserted at I+1. And then the second argument is the number of values inside the array that you want to remove starting from this point here, this index here. And we don't want to remove anything, so we're going to put in 0 here. And then the third argument is actually what do we want to insert? And we want to insert a new node, right? So we're going to put in new node. And then what are the x and y position? It is going to be this point, n1.x plus diff.x, right? So we get it to here. We add this vector with the new diff vector. Same thing for the y direction, n1.y plus diff.y. All right, and let's click run. And it gives us an error. And why do you think that is? It is because at I plus 1, when I is the last index, there is no I plus 1, right? So we need to find a way such that we can loop around the index. So I'm going to be using a modulo expression to fix this issue. So how it works is that a modulo is an expression that returns the remainder between the division of two values. So let me show you in a different sketch. So let's say that we have a value of, let's do 7 mod 4, right? Which means we get a return value of 3, and that is because it is giving us the remainder between the division between 7 and 4. So 4 goes into 7 one time and has a remainder of 3. But let's say that we do 1 mod 4. We get 1 because actually 4 cannot go into 1 any time, right? A remainder is just 1. So what we need to do is that, let's say that we have the index value that is the last one. So let's say that, actually let's start with the node's length, right? Say that the length is 10 and then the index, which go from 0 to 9, right? So this is the last one. So what we have is basically index plus 1, right? Which is 10, and there is no index of 10. And what we can do to fix this issue is we can do index plus 1 mod and then the length of the array. So if we do this, instead of getting 10, we get 0, which allows us to loop around the length of the array. And so this is what we're going to do. So we're going to do I plus 1, right? So this is the last index. And then mod nodes.length. So let's say that this is the other numbers, that's not the last one. It will give us the next index, which is correct, 6. All right. And I'm also going to do the same thing for this, just so that there is also no issues here. So let's insert index to be equals to I plus 1 mod nodes.length. All right, let's try this. Oh. Okay, it's not num, right? Because num starts at 10, but because we keep inserting more nodes, so we need to do nodes.length. All right, perfect. Now let's write some steering behaviors. So the steering behaviors are going to be cohesion and separation, and these are going to control the movements of the nodes, right? So if you have no idea what steering behaviors are, I also recommend that you look at the flocking simulation video to get a better understanding of that. I'm going to be writing two methods here, cohesion and separation. I want to start with separation because this is exactly the same as a flocking simulation example. We're going to start by first creating a vector called steering. So this is going to eventually be a steering force that we add to the acceleration vector. And then we're going to create another variable called total, and this is going to keep track of the number of nodes that we have to look at. So speaking of that, we need to also provide an argument or a parameter called nodes. Then what we're going to do is that we're going to loop through all the nodes. So let's use the for loop to go through I equals to 0 to I less than nodes.length I plus plus. So what the separation steering behavior does is that it makes sure that the nodes do not get too close to each other. So how it works is that it is going to look at the neighboring nodes, right, within the separation distance, which we're going to set as a variable. And basically, the closer the neighboring nodes is to you, to the current node, the higher the force or the higher the impact it has on you. So you want to get further away from the nodes that are closer to you, whereas the nodes that are far away from you, those has less impact. So you see how that comes into play once I start coding. Even though we're looking through all the nodes inside the nodes array, but the nodes that actually matter in terms of impacting the steering force is the nodes that are within the separation distance. So that's exactly what we're going to do. We're going to calculate the distance. So let's set a variable called distance, and it will be set to a function called dis, which will allow us to calculate distance between 2 points. So the first point is going to be this.position.x and this.position.y. And then the second point is going to be the neighboring nodes, right? So nodes of i.position.x and nodes of i.position.y. All right. And then what we're going to do is that, super long. Then what we're going to do is that we're going to write an if statement that says if the current node is not the same as the neighboring node and distance is less than separation distance. This ensures that we're checking the neighboring node and not itself, and also this neighboring node is within the radius that we want to check. And so actually let's go back to Sketch, and how about we create separation distance to be equals to, so I actually want the separation distance to be greater than the insert distance by a factor. So how about I just multiply it by 2, by a factor of 2. All right, so let's go back to node.js. All right, so once we have this, we're now going to actually create a vector called diff again. And basically this vector is going to be a new vector that points from the node's neighbor to me, right? So let diff equals to p5.vector.sub. And if it's pointing from them to me, then the first one has to be this.position, then the second one is going to be nodes of i.position. And as I said before, the closer you are to me, the more impact you have on me. So what I'm going to do is that I'm going to set diff and divide it by the distance. So distance square. So when you divide something by a large number, it means that the value is going to be a much smaller, right? Meaning that the further away you are from me, then the less impact you have on me. But if distance is very small, so if this value is small, then diff is going to be larger. And then once we have this, we want to add diff to the steering vector here. And then we're going to tally up how many of the neighbors we're calculating, basically. And then after we have the steering vector, next we're going to write an if statement again that says if total is greater than 0. So if there's more than one neighbor around it, then we're going to first divide this steering vector by the number of total so we can get the average, right? But this steering vector is currently a velocity. It's a desired velocity that shows the direction and magnitude at which my current node should be going. But what we want is that we want to actually find the steering force, because the current node has its own current velocity. This is the desired velocity. So we need to find the steering force that will actually helps move or push the current velocity to the desired velocity. And we can do that by subtracting the two vector. So steering dot sub of this dot velocity. So you can see that I show you two ways of creating or of subtracting two vectors. So this first one, right, you can see that I create a new, completely new vector diff by using p5.vector.sub, and then I provide two vectors, right? So we get a new, completely new vector that points from this vector to this vector. But this way, instead of creating a new vector, we basically updating the current vector, which is steering vector, by subtracting it with this dot velocity, and then we get the steering force, which is the value that allows us to bring the current velocity to the desired velocity. And we actually also want to add 2 additional pieces of code to ensure, as a precaution, to set the limit of the velocity and also the force. So the first one is we're going to put it before we change it to a force. So we're going to set the steering magnitude, and we can use the function setMag. We're going to set it to a specific speed. And then after that, we're also going to limit the force that we allows it to push, which is going to be set to steering.limit. We're going to limit to this dot max force. All right, so up here, we also want to set this dot max speed. I'm actually going to set it to 1 for both, and then we can change the values to see what it does. So now once we have this, what we can do is we can set the acceleration to the value of this steering force. Or the way that I'm going to do is actually inside update, we're going to set a new variable. Let's call it separation. And separation is going to be calling this separation method, right? And we're going to provide the nodes here. And then after that, what I want to do is that I want to add the acceleration vector with this separation method. And the reason I want to do this is because we will be adding separation, and then we'll be adding cohesion as well. All right, save. Okay, so let's go back to this one. We need to bring this back and then put in nodes as an argument. Let's see what happens. Whoa, okay. I think the initial acceleration I forgot to change. Okay, don't crash.
A few moments later.
Ah, silly me. I never return it. All right. Okay. A lot of crashing is happening right now. Okay, let's make this bigger to 50. All right, and you can see that it's super chaotic right now and is crashing. And one of the main reasons is that we actually forgot to reset the acceleration value. So right now, remember when I was printing out the acceleration value, it stayed constant at 1. But what is happening right now is that we're adding the steering force here to the acceleration vector, and we never reset it. So this value increases over time. And so it doesn't actually perform what we want it to do. So we're also going to set acceleration back to 0 every time the draw loop is called, so we can just multiply it by 0. And I hope that this fixed the issue. The difference is not super noticeable, but we need to ensure that acceleration is resetted here. Another thing that we want to do as a precaution is also in this update here, also set the magnitude to this dot max speed to make sure that it doesn't travel too fast, go overboard. And then what I want to do now is also actually draw a line between each of the points. So inside draw here, I'm going to comment out display actually, but I'm going to go through this for loop again. Nodes.length by ++, and then set the first and the second nodes. So n1 to be equals to nodes of I dot position, and then n2 to be nodes of I plus 1 mod nodes dot length dot position. And then I want to draw a line between the 2 points, so just use the line function. Do n1 dot x, n1 dot y, n2 dot x, then n2 dot y. All right, it works. It runs really slow. Guess that is also to be expected. So let's change some of these values. So let's do maybe 100 here, and then how about 10 here? See if yeah, not bad. Super slow. It's like much slower than I thought it would be. I mean, we'll be optimizing the performance later using the Quadtree, but it is even slower than I thought. All right, so now let's implement the cohesion method here. So when I say that it's a little bit different, that is because instead of looking at all of the nodes, or even just like within the radius of the separation distance, right? For cohesion, I actually just want to look at the two neighboring nodes, the one to the left and the one to the right. So it actually is still going to be provided with the nodes argument here. So we know what are the nodes inside this array. But okay, we're gonna start with the same thing, right? So create a steering vector and then also set total to 0. But now I want to find the index of the one to the left and then the one to the right. But we're going to start with the current one. So let's do this index. And we can use a JavaScript method called index of. So we need the array and then index of and then this. So now we get the index of this particular node. And then the next one is going to be, let's start with the next index. So this one is going to just be nodes of, no, so we're just doing the index, right? So it's going to be this index plus 1. Make sure that we need to wrap around, right? So mod nodes length. And then the next one is previous index. And you might have guessed that we could do index minus 1 mod nodes dot length. But you would be wrong because let's try it. So let's say that the current index is 0. And so 0 minus 1 mod node length. We get -1. And what we actually want is 9, right? So actually what we can do is we can add it with nodes length. And this way we do get 9. So that's the adjustment that we need to make. So we need to add it by nodes dot length. All right. And then after that, what we need is, we don't need a for loop like this anymore. All we need to do is that we just need to add it to the steering vector here. Steering.add. What are we adding? We are adding nodes of next index dot position and steering.add nodes of previous index dot position. So what the cohesion function does is that basically it takes the position of the two neighboring nodes, right? The left and the right. And then I'm going to find the middle point. And then basically that is the point or the position at which I want the current node to travel towards. So we want the nodes to be close to each other, right? To stay close to each other. So that's the way that we're going to do it. Find the average point between the two nodes and then have the current node to move towards that one. So once we do this, what we need is that we need to also tally up or not. So we just add 2, right? Because we want the average between these two nodes. And then similar to how we did this, what we need to do is that we need to write the if statement. Let's say if total is greater than 0, then we're going to first divide this steering by total, so we get the average, and then now we need to subtract it by the current position. So by subtracting it by the current position, we get a vector. The steering vector here becomes the vector that points from this position to the middle point here. But then we also want to subtract it the second time to actually get the steering force that will allow us to push or move the current velocity to the desired velocity. So we're going to subtract it by this dot velocity. And between each two of these, we're going to first set the magnitude to this dot max speed. And then we're going to limit the force with this dot max force. And then we're going to return steering. All right. And then inside update, we're going to do the same thing by first, let's set a variable called cohesion, and we're going to call the cohesion method here, providing nodes. And then inside here, we're going to also add cohesion. All right, let's click run. Ta-da! Okay. And now we get this natural pattern from the differential line growth algorithm, which looks pretty cool. Yay! Okay, but as you can see from when I even just tested the separation function, right, that it's running not the best. And I can prove that to you by, how about we just inside draw here, let's just print out the frame rate. Frame rate, see how it performs. Doing fine at first, and as we insert more and more points, and now it's running at like 15 to 20 frames per second instead of the beginning 60 frames per second. Now you get the idea of how to create these natural patterns, but to optimize the performance, we're going to be implementing the Quadtree data structure. First, we're going to add the file. Let's call it Quadtree.js, and make sure you reference the file inside index.html here. All right, and basically I'm just gonna copy and paste the Quadtree data structure JavaScript file that I have written, and you can see how I do that in the Quadtree video that I did for this series. We're gonna actually be creating 3 variables. The first one is Quadtree. Second one, let's do boundary. And then the third one is capacity. I'm going to set this to 10. So a Quadtree is a data structure that is used to organize data within a 2D or 3D space. We're going to be using it to organize a 2D space. And it does that by subdividing the space into subsections such that it makes it easy for us to find, to locate a point, and then to also access a point. And the boundary that you see here is going to be the size of the 2D space that we're going to use. And then capacity here is the number of points that we can have within a subsection before we divide it even more. All right, so inside setup here, first I'm going to set Quadtree to create a new Quadtree object, and we're going to provide 2 arguments, which are going to be boundary and capacity. And we have capacity set already, but boundary is going to be a new rectangle, which is also a class that we created in the Quadtree file, Quadtree JavaScript file. And then here we need to provide the x and y coordinates of the middle point of this rectangular space, which is going to be width divided by 2 and height divided by 2. And then the third and the fourth are going to be the width divided by 2 and height divided by 2 of the size of the space. So that's exactly what it is. So width divided by 2 and height divided by 2. And then what we're going to do is that we're actually going to be using the Quadtree to find the neighboring nodes, to actually use it as an argument for the separation function, separation method. Because right now, basically for the separation method, right, we provide nodes. So the performance is not great because the separation method looks at all of the nodes, even if it doesn't actually is inside the separation distance. So we're going to use the Quadtree to limit the number of nodes that we look at. And so to do that, I'm going to comment out this print function. So inside this for loop here, I'm going to first set the range. So the range is going to be a circle of the radius of the separation distance. So range is going to be a new circle, and we're going to provide the position of the current node. So nodes of I dot position dot x, nodes of I dot position dot y, and then the radius is separation distance. And then the next one is we're going to be creating an array called neighbors. So it's an empty array for now, but this is going to be an array where we're going to put the points that are the neighboring nodes. And then now all we need to do is that we need to call Quadtree.query, which is a method where we provide the range and the array neighbors. And then by calling this, then neighbors now is going to be storing the neighboring nodes. And instead of nodes here, we're going to be putting in neighbors. But actually, this update method, I'm going to do nodes, comma, neighbors, because I still want to use the nodes as the argument for the cohesion method. All right, so now if we go back to node.js, we need to do some update. So in here, for nodes, for update, we do nodes, comma, neighbors. And then for cohesion, we are going to use nodes. And then for separation, we're going to use neighbors. And then if I go to separation here, I'm going to change everything to neighbors. Neighbors, 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 neighbors. Oops. Neighbors, neighbors. I guess I can just have kept it as nodes and then just change, like when I apply this, I just do neighbors, but just wanted to make everything clear to make sure that I didn't miss anything. So with this, all right, let's go back to Sketch and let's uncomment this, save, and then let's click run. Okay, something is not correct with the Quadtree implementation.
A few moments later.
I forgot very important thing. So essentially right now, I basically just call all of these Quadtree query stuff, but I never actually put any points inside the Quadtree. Okay, so first what we need to do is, okay, so we're gonna write a for loop that goes from I equals to 0 to I less than nodes.length I plus plus, and then we're gonna insert the points into the Quadtree. So do Quadtree dot insert p of a point, but then we're going to create a point p to be a new point, and then inside point class here, what we need is we need x and y position and then the node itself. So we're going to do nodes of I dot position dot x, nodes of I dot position dot y, and then nodes of I. By writing this for loop inside the draw function means I keep adding the points over and over and over again, right? And so that's going to make the quadtree not actually function the way we want. So we also need to make sure that we do quadtree dot clear quadtree, and this helps us reset the points inside the quadtree. And then once we have all of this, then that's when we can actually call the query to get the neighboring nodes. And I actually, during the time I was trying to figure out this, I realized that I had a typo when I wrote the word neighbors. That didn't do anything, but now we corrected the typo. And also inside the update function here, instead of setting the magnitude of the velocity to a specific speed, this dot max speed, I changed it to limit. So that just means that we limit the velocity instead of setting the velocity to a specific value. So hopefully with this, then it should work. Let's try it. All right. Okay, looks like it's still at around 60 frames per second, and now our thing is trying to make these beautiful natural pattern. Okay, yay. All right, so now that we implement the quadtree structure, let's comment this out, and then how about we play around with this here. So try a different value. All right. Okay, so we're pretty much done, but I want to add two more things. The first one is a border detection. Basically, I want to create a border around like a rectangular or square shape so that the way that these pattern grows will be limited by that constraint. And then the second thing that I want to do is that I want to actually stop it from growing if it reaches a certain number of points. So yeah, okay. I'm gonna go to node.js here, and then maybe we do it up here. So let's do check borders. And this is just a regular border detection. So we're gonna write an if statement. Actually, first I'm going to create 4 variables. So left, right, top, and bottom as the limit. So left, how about we set it as a specific margin, which we'll create as a variable later. Right is going to be width minus margin, and then top will also be margin, while bottom will be height minus margin. And then we're gonna write an if statement that says if this dot position dot x is greater than right, then we're gonna set this dot position dot x to be equals to right. And then else if this dot position dot x is less than left, then this dot position dot x is going to be equals to left. And then I also want to make sure that the velocity of x is going to be bounce back. So just multiply it by -1 on both of these, and then we can just copy and paste this for the y. So this will be top y -1. Okay, so this will be if it's less than, no, I think this if it's more than bottom, and if it's less than top, then need to change this to all y. Okay, and then inside update, I'm going to call this dot, what is it, check borders. All right, and inside sketch here, how about we set margin to be, let's do 30. How about we do 50? so it's easier for it to grow faster. And I'm actually going to make the size of this to be smaller. Here, let's try this, just to give you a sense of how this works. So as you can see, it is limited by the margin that I set. Okay. All right. And then now the last thing that I want to do is that I don't want it to continue to insert over and over again. So let's do if nodes.length is greater than, no, if it's less than max points, then insert, and then else, let's do no loop. And basically no loop is just stopping it from calling stop the draw function to run. And then how about we just print, let's do max points reached. And then how about I set max points to, let's do maybe 3000, and let's move this back to 400. All right, let's try. It's gonna take a little while. All right, so this is basically maybe you should increase the max points, but this is basically how you can simulate the natural patterns using the differential line growth algorithm. And as you can see, I had the starting initial points inside a circumference, right, of a circle, but the starting points can be many different shapes. What if you do it based on a line? What if you do it based on the shape of a triangle? I really love these type of algorithms that allow us to create natural patterns. So I hope that you enjoy this one and give it a try.